Okay, so let's start. So what are we interested in today? So we are going to look at what are called as eigenvectors and eigenvalue. Okay. This is what we are interested in. And eigenvectors and eigenvalues, these are defined over square matrices. Okay. So and whenever I talk about a general matrix, I'm going to assume it's going to be an n cross n matrix. Okay. So this to keep not talk about. I mean, so anytime I talk about a matrix in general, I'm going to view it as an n cross n matrix. Okay. Now, because it's first of all it's a square matrix, I'm going to use n for the number of rows and the number of columns. Good. Give me a minute because there's some noise here. Okay, so let's start with an example. So I'm going to have this example. A is equal to what is example? Yeah, 1 minus 1 2 4. Okay, so this is one matrix I have, and let's look at. I'm going to multiply this matrix with a vector, and let's first consider some. Okay, let's multiply this with a vector. Let's say 2 1. Okay, so I'm going to multiply A with the vector 2 1, and you should tell me where it is. So where is 2 1 going to be? So this is 1, this is 2, and this is 1. So 2 1 might be somewhere here, right? This is my this is my 2 1 point, right? So if I multiply with so 8 times 2 1, what do you get? Someone can tell me the answer. Yeah.
2 minus 1, 4, 4.
So 2
minus 1, 4, 4.
So sorry. What is the answer?
2 minus 1. Oh, sorry. Wait, I messed up.
Sir, 1 and 8.
So it is 1 times 8. 1 8. Yeah, sorry. 1 8. So see, I don't know what happened. So it's 2 1, right? You multiply 2 1, so it's.
Yes, sir, sorry.
How do we do this multiplication? So this multiplication is, this is 2 times 2 plus 1 time minus 1 4. Okay, and this is what I just forgot. It's 1 8, right? Yeah. So that's 1 8. Okay, and so that means, so this vector, once I multiply, this vector is taken from here to somewhere here, right? So this vector, right? So A takes you there, right? So this is X, This is the vector x, and ax basically takes you to this point. This is clear, right? And this is called as a linear transformation. Okay. Now, so in some sense, the point x has been transformed from this point x to this point y, and it's a linear translation. Okay, so that's why it's called linear transformation. Okay, now I hope this much is clear. But we are interested in something, some special kinds of vectors for this matrix A. I don't. So this matrix, as you could see, has changed the direction of these two vectors. This vector 2 1, right? So the direction of this vector 2 1 is basically this, right? This is the direction of this vector 2 1, and A times this vector x, ax has basically is not in this direction. It has changed it to some other direction. I mean, basically this, right? But what are we interested in? We are interested in that particular vector whose direction is not changed after multiplication with A. That's what I'm interested in, right? So let's look at this vector. I'm going to multiply 1. So what is it? 1, 2, minus 1, 4 with the vector. What's the vector I have? Yeah, 1, minus 1. Okay, so I can, let me draw this here again. So it's 1. So it's 1 and minus 1. So it's basically here. This is my vector 1 minus 1. And I'm going to multiply, put it in some color. Yeah, 1 minus 1. So this matrix, so I'm going to multiply this vector with A. What do you get?
Two minus two.
So it's 2 minus 2, right? And where is that in this picture? In the same direction as 1 minus 1, right? And somewhere here, this is my 2 minus 2. Right? So this is, if I rewrite it, this is 2 times 1 minus 1. Okay. So it's in the same direction as this 1 minus 1, and that's the most crucial, the most important factor I was looking at. So what, okay, once again, what was it I am interested in? I am interested in finding that particular vector such that when A is multiplied with that particular vector, the direction won't change. Okay, and here we can see that A times 1 minus 1 is going to be in the same direction. It's just that it is multiplied by 2 times. Right? Is that clear? Okay. This is called as, so this is called as an eigenvector of A. Okay. And this magnitude, this value is called the eigenvalue. Okay. So this eigenvalue corresponds to this eigenvector, and this eigenvector corresponds to this eigenvalue. It's clear. Okay. So if I formally say what is an eigenvector and an eigenvalue, you should think of Ax. This is, we will write Ax is equal to lambda x. Here, x. This is the eigenvector, and this is the eigenvalue. Right. So I hope this much is clear. So in this matrix A, I know one eigenvalue, which is 2, and its eigenvector is this 1 minus 1. Now, can you tell me another eigenvector in the same direction? Is there an eigenvector in the same direction? A different eigenvector in the same direction? Do you have that?
Yes, sir. It would be 2 comma minus 2.
Yeah. So the point is that because it's see, eigenvector in some sense is talking about the direction, right? So any vector you take in the same direction, I could have taken 2 minus 2 or 3 minus 3. Any such vector I take, if you multiply, you can just let's just see that. What happens if I do? Let me do this. So what happens if I do 1, 2, minus 1, 4 with 1 minus, 3 minus 3? What do I get? I will solve it myself. It's going to be 6 minus 6. Okay. Yeah. So I wrote the answer, but now let me just verify it. So, first entry is 3 plus 3, 6, and the second entry is 2 into 3, 6, minus 12. So it's 6 minus 6, right? So this is correct. And this is same as this is equal to, this is again 2 times 3 minus 3, right? So again, it has doubled this eigen vector. So that's right. Okay. So I could have picked any vector in this direction of this eigenvector, and this matrix is going to double that. This here. So in some sense, you should think of eigenvectors as a direction and eigenvalue as the magnitude, which is right, a magnitude of change. Okay, right. So so it's sometimes when people ask you, so usually when people might say that, okay, there is only one eigenvector, right? So in that, when people say like that, or there are only two eigenvectors, when people say like that, they intend to mean that there's only one independent eigenvector, right? Because I know that there are like infinitely many eigenvectors, but they are all dependent. In this case, now as you could see, the same line, if I take there are infinitely many eigenvectors, but they are all dependent. There is only one independent eigenvector in this direction. So when people say there is only one eigenvector, they usually mean there's only one independent eigenvector. Okay. Right. Now, so this much is clear. Now, what is the next thing? So the next question is, I'm given a matrix A, and I am asking you to find out. So first question is that something you will soon see, or maybe some of you already know this fact, that this is not the only one eigenvector and eigenvalue of this matrix. In this example, we have found out one eigenvector 1 minus 2 and an eigenvalue 1 minus 1 and an eigenvalue 2. But as you would soon observe, this is not the only eigenvector and value for this matrix. Now, so the question is, how do I find out the eigenvector and eigenvalue? So that's the question we are going to address. Now, because in general, it may not be easy to see. So here, somehow I was able to find this 1 minus 1. Right? But in general, how can I do this? So that's the question. So now, what do we do? So I'm looking at a matrix A, and I'm finding this x and this lambda, right? So what do I want? I want an x and lambda such that A is equal to lambda x. What I will do first is I'm going to write lambda x as, I'm going to rewrite this as Ax is equal to lambda I times x. Okay, so this is same as why can I do that? Why can I write that? It's because What is lambda I is the identity matrix. So this is basically I'm talking about something like this. This times vector x. Okay. So if I do this is x1 to xn. This is my vector x. Now you can observe that this is same as lambda x1 up to lambda xn. Okay, why can I do that? This is all 0.
Sir, your voice is breaking a lot,
Oh, you can't hear this?
at least to me.
Okay.
Yes, sir, for me as well.
Okay. What to just one second. Let me see what can. Okay, can you hear now? Hello? Hello?
Slightly
Yes,
better.
sir.
Yes, sir.
Okay. So what I was trying to tell is that you can rewrite lambda x equal to lambda x as x equal to lambda I times x. Okay, because lambda I is this lambda on the diagonal of I. So you know identity matrix is 1 on the diagonal. Lambda is basically lambda on the diagonal of I. So that right, it's a diagonal matrix, and this lambda I times x, the vector x, is same as x. This is what I'm trying to say. Since you can, so if you don't get why this is true, just go and work it out. You should be able to see this. Okay. Right. And since this is the case, ax is equal to lambda ix, you can rewrite this as ax minus, sorry. Yeah, so you can rewrite it as ax minus lambda I times x is equal to 0. It's a 0th vector. I put a bar on top to denote that it's a 0 vector. That means all entries are 0. And therefore, you can rewrite this as a minus lambda I times x is equal to 0. Okay. Now, when can this be 0? When can this happen? When can this happen? So I am saying so this is a matrix. You can think of this as a matrix P. Okay, and I'm asking when can x be equal to 0? When can this happen? Hmm?
When x is 0.
So one case is when x is the 0 vector. This is one case. Actually. This is not the interesting case we are looking at. Okay, so x is 0, clearly you can, whatever you do, you're going to get bx equal to 0. Right. But we are looking at another interest when x is not equal to 0. Is there some vector which is not equal to 0, but this a minus lambda I becomes equal to 0? So a minus lambda I times x becomes equal to 0.
Is of the form lambda I for some lambda like 2 0 0 2 0 0 0 2.
It's of the form.
When
A
A
is of the
minus,
form
Sorry, 1%.
A is of the form lambda I. So
A is of the form lambda I. So you're saying the matrix B is 0.
yes, sir.
Yeah.
when rows of A minus lambda I are Li.
So
LD.
matrix. Okay. So this is another claim which is saying matrix B is 0. Good. But these, yeah. So you have picked out all the kind of
Sir,
uninteresting case, and we
sir,
have. Huh.
when the rows of this vector matrix B are perpendicular to this x, that is their dot product is 0.
Okay. Okay. What is perpendicular to what?
The
You have the
rows of B, huh?
rows of B are perpendicular to this vector x. Yeah. So that. So. So rows of B are, I'm going to denote this as perpendicular to x. Okay, so so this symbol is perpendicular. Okay, to x. Good answer. This is correct. Yeah. Any other? So the same property you can tell. Yeah, I mean, but when can that happen? That's the main question. When can it happen that all the rows of B are perpendicular to x? When can that happen? Can it even happen? Can it happen for some matrices? Can it really happen that there is a vector x dot product with all the rows of that matrix B gives me 0? Can it really happen? Let's see. Maybe my suggestion is let's look at an example, and I'm going to give you an example, and from there you should tell me when this is possible. Okay, so I'm going to give you a matrix like this. This is my matrix B. Can I tell does there exist an such that it gives me 0? Hmm? Hello, anyone there? Does there exist an such that Bx equal to 0? Is anyone?
1 minus 1.
So 1 minus 1.
One. It was so trivial that you are all uh, reluctant to answer a trivial question. Is it? So yeah. So why is 1 minus 1? 1 minus 1 you can get 0. Hmm. So this matrix I can get a vector x, but why was I able to get a vector x such that Bx equal to 0 here? I'll give you another matrix.
So rows of B are in the same direction, all the rows.
Okay. So so this is a good claim. So you are saying rows of B, so B are in same direction. So what do I mean by same direction? So another way to rewrite this is saying that rows of B are, it's not exactly the same, but this is the better way to, okay. Rows of B are dependent. Okay, so I mean, if two rows of B are in the same direction, obviously they are dependent. But if there are multiple rows, they need not be in the same direction. But if they are dependent, you can do this. Why is that? Can you do that? Why is that? Why is it even possible? Is it really about rows of B are dependent or columns of B are dependent? Shall I talk about columns of B are dependent? Can I say that? What do I mean by saying that columns of B are dependent?
So it means that you can find a combination of the values in the vector x such that if we take the linear combination of the columns of B, then we'll get 0.
So let me just write this as my columns B1, B2 up to Vn, right? And someone is telling me that the columns of B are dependent. And so what does that mean? So it means there exists.
There exists x1 to xn.
Shall I write C1, C2?
Yes, sir, sure.
C1, C2 to Cn such that?
C1 into V1 till
C1 times V1 plus C2 times V2. This is
0.
This is 0. Right. I write this thing in a matrix form, or in the kind of form we are writing this. Can I write this in a better way? V1, V2 up to Vn. V1. This is the way to write this. Yeah, this is why I have been talking about how do you see a matrix vector multiplication, right? How do you multiply these two? Let me just write. Let me give you a 1, 2, 3, 2, 1, 5, minus 1, minus 2, 0, times 1, 2, minus 1. How do you do this multiplication?
So it's 1 times the first column, 1 to 3.
Yeah, so 1 times first column. So this is another way which we have been talking about to see matrix times a vector. So this is a very important way to see multiplication. Okay, so this is same as this is how you have to see. So this is matrix A times a matrix X. Okay, and this is how you see matrix multiplication. And if you see it this way, what is this? What is this happening? What is this? This is, so these are vectors. See? Okay. What is this? This is, how do you see this matrix multiplication? This is C1 times V1 plus C2 times V2. Okay. Is it clear? No?
Yes, sir.
Yes, sir.
Okay. So when I am saying these vectors V1 to V, see, if things are not clear or you have any doubts, stop me and get things clarified. Okay, so we are just looking at linear algebra, and this is basically the foundation. So without a strong foundation, the building will collapse, right? So yeah, so to clarify, if you have any doubts, just ask me and fix your foundation. Right. So what is it? So what are we saying? So I'm saying if the columns of B are dependent, then there exists this constant C1 to Cn such that I can multiply this matrix B with this vector to get 0. Right. And what if the columns of B are not dependent? So if columns of B are not dependent, what can we say?
Sir, all C has to be 0.
So there, okay, I'm going to write there do not exist. So you want to say first this thing, and okay, such that C1 to Cn, I have to write that this is not equal to 0 also, right? So this is not the 0. This entire thing is not 0. So that, okay. So if columns of B are not dependent, then I mean, the only way you can make this 0 is by taking all CAs to be 0. That's the crucial factor. Now let's go back here again. You want to rub this thing, entire thing over. Now you should tell me the answer. Okay. So we are back again to this question. When is Bx equal to 0? And we have already taken care of the first case where, okay, x 0 vector. What is next? What else can other way? What can be other reason when Bx equal to 0 can occur? Yeah, who wants to answer that? NS. Yeah, so when is Bx equal to 0? Yeah, what is happening? Yeah, who's this? Anmol, yours. Anmol, can you mute? Yeah. Okay, so let's go back. So who can tell me the answer? So when can this be 0? If x is equal to 0, when can this be 0? I mean, what is it we were discussing? We were saying.
X is like the eigenvector of E.
Just look at this. We have a matrix B, and I am asking you, can I find a vector x such that Bx equal to 0? When is this possible?
So for a non-zero x, that is possible when columns of B are dependent.
Yeah, exactly. This is possible when columns of B are dependent. This is what we have been telling. So if columns of B are dependent, I can find these constants C1 to Cn such that I multiply with this vector, B times that vector gives me 2. And the other is also correct. When is true, that is when columns of B are independent, you can't find something. It's only possible when the vector x is going to be 0. Okay. So the crucial factor is that this is possible when the columns of B are dependent. That's the main crucial factor. Okay. Is there some other way? Okay, now I give you a matrix B. And you need to find out whether the columns of B are dependent. How can you do this? What are the other things we have seen? What do we know about? So this is an n-cross-n matrix, okay? So just like we have been telling, our matrices are going to be n-cross-n. And B is an n-cross-n matrix. And I know that the columns of B are dependent. Can I say this in a different word? Is there some other? So I am interested in checking whether the columns of B are dependent. Is there different way to?
So you can say it in terms of the rank.
Okay.
Invertibility.
Right. So this is another way to check is that rank of B less than good. Now, is there any other way? So is there any other way? When if rank is less than n, what can you talk?
So
what
determinant of B is 0.
So or determinant of B is equal to 0. So see, these are all similar. I mean, they're all equivalent notions. Okay. Right? Or you can write or when rows of B are dependent. Okay, so these are all equivalent notions. But what is the most crucial? So what is that thing which we can use here? We can use this fact: determinant of B is 0. This is the thing we can check now. Okay, I'm going to use this fact: the determinant of B is 0, or I'm going to check whether determinant of A minus lambda I is equal to 0. In other words, what values of lambda will give me determinant of A minus lambda I to be 0. This is what I'm going to use now.
Sir, your voice is breaking a lot to me.
Oops. Okay. Let me repeat what I was telling. So tomorrow I will go to the institute. Today I'm at home. Okay. So let me repeat what I'm saying. I'm saying where will be? Yes. So I was telling that there are columns of B are dependent means this is equivalent to saying the rank of B is less than n. This is equivalent to saying that the determinant of B is 0. This is also equivalent to saying that the rows of B are dependent. Okay, these are all equivalent notions. And most important factor we are going to use the fact that determinant of B is 0. This is what I'm going to use. And determinant of B is equal to 0 means determinant of M minus lambda I is equal to 0. Okay. So determinant of A minus lambda I is 0. We know how to find the determinant. And I'm going to use this fact. I am interested in finding those lambdas which gives me those lambdas such that A minus lambda I, determinant of A minus lambda I gives me 0. Right. Let's do that. Will give me all the lambdas which makes the determinant 0, and this will give me the eigenvalues of this matrix. That will give me the eigenvalues of A. That's a crucial factor. We started off all these things, find out the eigenvalues of this matrix A, and what we are saying is that okay, the eigenvalues of A are those eigenvalues, are those lambdas such that the determinant of A minus lambda is 0. That's what I'm telling. Now let's look at an example and find out this. So I'm going to give you this matrix, and you should now tell me this. So 1 minus 1 4. This is the matrix we started with earlier. This is my matrix, and I'm going to have. So I'm interested in A minus lambda. So what is I? I is so lambda times 1 1 0 0. Right, which is same as writing. So 1 minus lambda minus 1 2 4 minus lambda. This is my matrix B. Okay. This is B. Right? Because this is equal to A minus lambda I. I'm saying that determinant of this is 0. Now, can you tell me those values of lambda which makes determinant of B to be 0?
2 and 3.
What values of lambda makes determinant of B 0? Yeah. Just let me just quickly write. The determinant is 1 minus lambda times 4 minus lambda. So minus of minus 1 into 2, which is minus 2. Right? So this, if we do this, we are going to get lambda square minus 4 lambda minus 5 lambda 4 plus 2 6. Right? This I can rewrite it as this is determinant of B, right? So this implies this I can rewrite it as lambda minus 3 times lambda minus 2, right? Is it correct? No, lambda minus 3 plus, yeah, this is equal to 0, right? Okay. So clearly now we know the answer, right? This implies that determinant of B is equal to 0 when lambda is equal to 3 and lambda is equal to 2. Clear? So what did we get now? So we have got the eigenvalues of A. So eigenvalues of A are this is what we have got. Okay, so let me just recap what I just now do. So what did I say now? We just now told that the eigenvalues of A is equal to all lambdas such that determinant of A minus lambda I is equal to 0. Good. This much is good. Now I'm interested in next question. I'm interested in is give me eigen vectors of A. Okay. So what
Sir, I
are
have a doubt in the first part.
yeah.
Sir, how are we sure that these two eigenvalues don't correspond to linearly dependent eigenvectors?
We don't know that fact now.
Okay, sir.
We don't know that fact now. We are just now telling the only point we have found out till now is the fact that these two are eigenvalues of A. Okay. Yeah. So let's now go back to our matrix A, which is again what was the matrix? Yeah, 1 minus 1, 2, 4. This is my matrix, right? And I know this fact A. So let me call this as lambda 1, lambda 2. Okay. This is usually in books, lambda will be, eigenvalues will be denoted by lambda, and lambda 1, lambda 2 will. So lambda 1 will represent usually the largest eigenvalue, and lambda 2 the second largest, lambda 3 the third largest, etc. Okay, that's the standard usage. So we will also follow that, and lambda 1 is equal to 3 and lambda 2 is equal to 2, right? Because those are the values. Okay. Now I have this eigenvector. Yeah. So I'm interested in finding out the eigenvector x that Ax is equal to lambda 1. So the eigenvector x which corresponds to the eigenvalue lambda 1. Okay. So this is same as writing A minus lambda 1 I x equal to 0, right? This is what we said earlier. Is what we saw earlier. So we are interested in finding out that vector x, which makes a minus lambda 1 I to be 0, right? Okay. So let's this is my matrix B. And what is the matrix B now? Matrix B for B for lambda 1 is equal to yeah. So first, okay, B for lambda 2. Okay, let's first do it for 2 because we already saw this how to do it. We already know the answer to this. So B for lambda is equal to 2, and I'm going to write. So this is so what is my B now? So which gives me B to be 1 minus 2, right? Minus 1, 2, 4 minus 2, which is minus 1, 2, 2. So what is the eigenvalue corresponding to this? Eigenvector corresponding to this?
One minus one.
Yeah. So this is something we already saw, right? We solved this earlier. We said that yeah. So this is an eigenvector for this matrix A. We already saw this, and for this eigenvalue 2. Now let's do now for lambda 1 is equal to 3. So now A corresponds to what is A? What is my B? B becomes 1 minus 3 minus 1, 2, 4 minus 3, which is minus 2 minus 1, 2, 1, right? Okay, what is the eigenvector corresponding to this?
Minus 1 comma 2.
Okay, so now so eigenvector is what is the answer?
Minus 1 and 2.
Minus 1, 2. Okay, let me see. This becomes 2, 0, minus 2. Okay, so let me now to recap what are we saying. So the eigen values for A are lambda 1 is equal to 3, lambda 2 is equal to 2, eigenvectors, the corresponding eigenvectors. Okay, so I'm going to write the to be corresponding eigenvectors are minus 1, 2, and 1 minus. Is it clear? Okay. Do you want to solve some more examples, or should we continue?
You can continue, sir.
We shall continue. Okay. Now, let me see the book. Okay. Now, we saw some properties of. Let me look at. So, what was the matrix A? I'm going to write matrix A again. Matrix A. This 1 minus 1. This is my matrix A, and we now know its eigenvalues and eigenvectors, right? So let's look at the following two properties, which are very crucial to properties of this matrix. So trace of A. Okay. So the trace of a matrix is basically the sum of its diagonal entries. Okay. What is that? It's 5. Do you see this 5?
Yes, sir.
Yeah. What is it? So the trace of A is a sum of the diagonal entries. So which is 5 for this matrix. And if it has it got something to do with the eigenvalues, you can see that the sum, that's exactly the sum of the eigenvalues also, right? So this is some an interesting property, sum of eigenvalues. You can see both are is equal to 5. Okay. Now let's look at something else. The determinant of A is, what is the determinant of A here?
6.
6. And what is the connection with the eigenvalues? Can you see that?
Product of the
Product.
The
eigenvalue.
product of the eigenvalues. Right, exactly. This is some beautiful connection between eigenvalues and the trace and determinant of the matrix. So this is some property you should keep in mind. Okay, the sum of the diagonal, because this helps you to find out the eigenvalues much faster, etc. I mean, especially in any competitive exam, to finding out the eigenvalues, this might be a much easier way to find out the eigenvalues than going to the kind of which we just now told. Right. So the trace, the sum of the diagonal entries is the same as the sum of the eigenvalues, and the determinant of the matrix is the product of eigenvalues. Okay. Two crucial. This is something. Okay. We see this in this example, and this is true for all eigenvalues. Okay. Now, next, another property. Another property of eigenvalues is the following fact. So there are n eigenvalues. Okay, with repetition. So there are, for an n cross n matrix, there are going to be n eigenvalues with repetition. Why is that true? Because we know the fact. Why is it true? Because we are interested in doing this, right? I am interested in, where is it? I'm interested in finding out the determinant of A minus lambda I. So any A minus lambda I is going to look like this. If I have a very large matrix, n cross n matrix, it's going to be something minus lambda here, something minus lambda here, up to something minus lambda here, and some values here. This is how a matrix is going to look like. And when you find out the determinant of this matrix, this might be, if you find out the determinant of this matrix, this lambda is going to come up. It's going to be a term. It's going to be a term of some lambda raised to n. Okay, and now, and since it's a polynomial, so if you don't understand it, you can skip it. So since it's a polynomial on degree n, it should have root, and therefore there will be n solutions to lambda. Okay, so that gives me there are n eigenvalues for this matrix. So, but there can be repetition. So there can be eigenvalues which repeat. Okay. Now, so someone asked me this question. Oh, but can it also mean that there are n independent eigenvectors? Does it mean there are n independent eigenvectors? That is unfortunately not guaranteed. There are these. I mean, I don't like those matrices, but what can we do? But there are such matrices. So let me call. There are some ugly matrices which do not have n independent eigenvectors. Okay, but most matrices have independent eigenvectors, but there are a few which do not have any independent eigenvectors. We soon see one example. Okay. So now another trick question. Let me ask you: what is the can you give me give me eigen values of A transpose? What would be the eigenvalues of A transpose?
It will be the same.
It's the same as the eigenvalues of A. Why? Because determinant of A lambda I is same as determinant of A transpose minus lambda I. You can see this fact because A minus lambda I is basically, if you have a matrix like this, it's something minus lambda here, something minus lambda here, up to something minus lambda. This is my A, and A transpose is so this is my B. Okay, and this is my this turns out that this is also B transpose. So B transpose, because as you can see, it's only the diagonal entries which has this minus lambda. Okay, and so A minus lambda, so B is A transpose minus lambda I turns out to be B transpose. And you know this fact that determinant of B is same as determinant of B transpose, and therefore the same lambdas make both of them 0. Therefore, the eigenvalues of A and eigenvalues of A transpose are the same. Okay, but I'm talking about the eigenvectors. Okay, eigenvectors can be completely different, but it's about eigenvalues. They are the same. Right. Now let's look at certain example matrices. And okay, so here is an example. Identity matrix. What can you tell? What can you tell about the eigenvalues and eigenmatrices, eigenvectors? Any idea?
1 to the power n, like 1 n times.
Okay, so the eigenvalues are 1, 1, n eigenvalues. What? Why can you say that? Yeah. So, okay. And what about the eigenvectors?
So the column vectors itself.
Sorry, here.
So the column vectors themselves are eigenvectors.
That is true, but that's not the complete truth. The complete truth is that any vector is an eigenvector. Why? Because an eigen matrix times x is same as 1 times x for any vector, right?
Yes, sir.
Yeah. So any vector is an eigenvector for the identity matrix. Okay, and it has n repeated eigenvalues, and any vector is an eigenvector for good. Now, let me go take another example to matrix A has rank less than n. Can you one eigenvalue? Is it tricky?
So could you please repeat the question?
Can you give me one eigen? Okay, I have a matrix A, which is an n cross n matrix. A is an n cross n matrix. but I give you the fact that the rank of A is less than N. Now, can you tell me about at least one eigenvalue? This, so I'm saying this already gives me one eigenvalue.
0.
0. Why? 0 is correct. But why are you able to say that?
I think we can reduce it to row echelon form, so one of the rows becomes 0. Something of that. I'm not entirely sure.
Okay. So many different ways we can see this fact. Why? What's the determinant of A?
0.
Zero.
Determinant of A is 0. And what do we know about determinant and eigenvalues?
Product is
Of the
0.
eigenvalues is equals the determinant of A. So determinant of A is 0 implies product of eigenvalues equals 0. What that means? So it has to be at least one eigenvalue which, right?
Yes, sir.
That's one way to see it. Now I will tell you another way to see it. I'm asking AX is equal to lambda X. I'm asking for this, and I know that the columns of A are dependent. So this is something I know. Columns of A are dependent. What do I? Again, what does that give me? That tells me that there is a vector X, right? There is a vector X. Such this is equal to gives me the 0 vector. So that or otherwise I can write it like this, right? Because the columns of A are dependent. Why can I say that? Because the rank of A is less than A. Implies the columns of A are dependent, and since columns of A are dependent, I can write Ax equal to 0 times X, right? Because Ax equal to 0. I know that Ax equal to 0. There exists an X such that Ax equal to 0, right? Ax equal to 0. Therefore, this I can write it as Ax equal to 0 times X. And this means that, again, this 0 is my eigenvalue, and this X is my eigenvector. That vector, which when you multiply A times that vector, it gives me 0. This is another way to see it. Okay. Now, let's look at third example. I'm going to look at a diagonal matrix. What are eigenvalues and eigenvectors? Can you tell me?
The diagonal elements are
Diagonal elements. So what is my lambda? What is lambda 1? Lambda 2, 2. What is the corresponding eigenvectors and eigenvalues? The eigenvectors corresponding to these values.
There's 0 only.
0, 1 here. And here.
1, 0.
Huh? Okay, so this is 1, 0. And why am I writing that? So let's just solve it. 0, 3 times 0, 1. Can you solve it? So this is same as, okay, let me write it again.
0,
so that
3.
Yeah, so I'm going to write this again so that you come to terms with this way to see it, multiplication. So this is 0 times 2, 0 plus 1 time 0, 3. Okay, and this is 0, 3. Right. It's clear? And what is this? This is 3 times 0, 1, right? Again, this is my
Yes, sir.
lambda 1. And this is my X here. Okay. This is my, we usually say, we usually denote by V1. to be the first eigenvector. So I'll call it V1 here. Okay. So if even if I had extended this to, let me make it a bigger matrix, a diagonal matrix. 2, 1, I don't know, minus 2, 0, 0, 0, 0, 0, 0. What are the eigen vectors and
2,
eigen?
1, minus 2.
Yeah, again, lambda 1 is equal to 2, lambda 2 is equal to minus 2, and lambda 3 is equal to 1. Okay. So one reason why I wrote lambda 2 is minus 2 is the fact that we order the lambda in terms of the absolute value. Okay. So it's just a convention, right? You can, the convention people follow, and so okay. So the lambda usually ordered in the absolute values of the eigenvalues, right? And you can see that the values and order the corresponding eigenvectors 0, 0, 1, and 0, 1, 0. These are the eigenvectors corresponding to each of these eigenvalues. Right. So eigenmatrix, if I give you the eigenmatrix easily, you can tell me what its eigenvalues and eigenvectors. How can I check these are? I mean, is there some sanity check I can do? Yeah. Look at its trace. The sum of its diagonal elements, 2 plus 1 plus minus 2, it's same as the sum of the eigenvalues, 2 minus 2, 1. Something we know that they have to match. What about the other thing? It's a determinant. What is the product of a diagonal matrix? Determinant of a diagonal matrix is the product of its diagonal element. And this is same as the product of the eigenvalues. Good. They have a match. So there are some sanity checks you can always do. Because if someone asks you to find the eigenvalues, eigenvector, and you found out these things, but maybe you need to have a second check whether what you did was correct. So you can do is quickly do the trace of the matrix and the your eigenvalue. Check whether they are the same. If they are the same, okay, good. That's one sanity check. What is the next sanity check? Find out the determinant of the matrix. Find out the product of the eigenvalues. They have to be the same. Good. Easy. Okay. So now you know how to solve objective questions. If these kind of things come in objective questions, you have to solve. You just have to look at each of the answers and find out its whatever trace, and I mean you compare the trace and some of the eigenvalues. This, I mean, some to solve. What do you say? Gate questions. So this is okay. This is about diagonals. Now let's go to next kind of. So here is an interesting thing. We'll finish off with two more examples, right? Here's a question. This is a little tricky. Okay. Now I'm going to talk about rotation matrices. We know what is a rotation matrix. What is a rotation? So let's get a 2 by 2 matrix. This is. So this is a matrix which rotates a vector by theta degree. So if this is your x1, this is my y, and this is x, and here is my vector v. Once you do, so I'm going to call this A. This is AV. Okay, and this is going to be theta. So that's rotation matrix. This is something we saw earlier. You can come up with this rotation matrix for any theta. You can do this thing. So when theta is 90, so you can rotate 90 degrees. So let me write the rotation matrix for theta equal to 90. What is the rotation matrix for theta equal to 90? Someone wants to tell me that? When theta is equal to 90, that is, you want to turn any vector by 90 degrees.
0, 0,
0,
0, minus 1, 1, 0.
0. Yeah. So this is the matrix for rotating any vector by 90 degrees. Okay. Now I am asking you, what is the eigenvalue and eigenvector for the matrix? See that? Can you see that? Is there something which is troubling? See, what is an eigenvector? What is an eigenvector going to be? So in eigenvector is something which I am saying that. So this is my xy. What is it I am interested in finding? I am interested in finding out a vector v. I am talking about the eigenvector. I am interested in finding out a vector v such that when I do AV, right, I am in the same direction. That's an eigenvector. An eigenvector is supposed to be pointing in the same direction after you do the multiplication. It's just that maybe the magnitude might have changed, but it has to be pointing in the same direction. That's an eigenvector. What does the rotation matrix do? Rotation matrix is going to rotate it. Rotation matrix, so here this is 90 degrees. So it's going to turn this vector, any vector you give, it's going to turn it by 90 degrees. Right? So this is now troubling. So what is the eigenvalue and eigenvectors for these matrices?
Theta equal to n times 2 pi.
Huh?
Theta equal to n times 2 pi.
No,
For any n.
I'm taking theta to 90 degree now. It's fixed. So this is my matrix A. This matrix is now fixed. Okay, and so any vector I take, so any vector, so A, so A times B equal to turned by 90 degree. Okay, and but now I'm asking you to give me eigenvector and eigenvalue for this matrix. And if I'm asking for an eigenvector, it says that okay, the direction should not change in an eigenvector, right? You can't rotate it. So what do we do? So does it really have an eigenvector and eigenvalue?
So theta will be 0 degree.
No, I'm saying okay. I have fixed the theta to be 90 degree.
No real value.
Okay. I fixed the theta to be 90 degree, and this is my matrix A. For theta to be when theta is 90 degree, this is matrix A, and I am asking you what is the eigenvalue and eigenvector for this particular matrix. Okay, so theta is fixed to 90 degree. Now, forget about theta and just assume that I have a matrix which rotates any vector 90 degree. And I am asking you to find out the eigenvector and eigenvalue for this matrix. And okay, so let's. Did someone try to find out the eigenvalue for this matrix?
Plus minus I.
Huh?
No real value, sir. Plus minus I. Iota.
So okay, so someone. If you do this, so I want determinant of this to be 0, right? And that turns out to be it's minus lambda the whole square, right? Plus 1 is equal to 0. You can just try this thing out. This basically is lambda square plus 1 is equal to 0. In other words, lambda is equal to plus minus I, right? Okay, so lambda 1 is okay. So this is where you have to understand that this again the kind of matrix we are not really interested in, because this matrix is saying that it goes into the complex plane. Okay, so and in fact it's saying that okay in the real for real it cannot do. I mean there is no eigenvector in the real space. because finally it's fundamentally it's a rotation matrix. So any vector you give me the else it's going to rotate that vector. So its eigenvector and eigenvalue you can find out only in the complex plane. So that's what the thing. So, we can just see that. So what I? So 0 minus 1 1 0 times some vector gives me I times x. What is that? So in media, so let me, this is minus lambda, so minus I, right? And minus 1 1 minus I. So this is this x gives me 0. What is this? What gives me this? What about 0? What about I? Oh, okay. So what about if I take 1 and I? 1 and I take 9. Yeah, so is this correct?
Yes, sir.
This is correct, right? So I'm going to do minus 1 I, right? This should give me 0. So I think Devani has agreed that this is 0. Yeah, let me just check. So how do I take this? Minus I 1 plus. So this is plus and minus 1, and this is, I can remove it, and this is minus I, and this is minus 1 plus 1, right? This gives me 0, right? Okay, so the eigenvector corresponding to, so eigenvector corresponding to lambda 1, which is equal to I, is minus I. Okay. Right. So this is something crucial factor that so the eigenvectors and eigenvalues can be in the complex plane, and these are matrices which we are not. These are things which we will. I mean, these are not matrices which we are going to work with soon. We will soon see these. We won't be having these kinds of matrices. Okay. Now, so finally the last kind of matrix. Here is a matrix. A is equal to 1 1 0 1. Can someone tell me its eigenvalues? What are the eigenvalues?
One, one.
1 and lambda 2. So if I know the eigenvalue, one eigenvalue, what is the other eigenvalue? It's easy to see.
Yes, sir.
Yeah, what is the other eigenvalue?
1.
1. Yeah. Okay. Right. And here's the thing. Okay. We get the eigenvalues of the eigenvalues of the diagonal entries of a diagonal matrix are basically those in the diagonal entries. But it's also true about what we have here. These are upper triangular matrix. Okay. This is my diagonal, and only those above this diagonal are are not zero, and those below are zero. So this is a diagonal matrix, and diagonal matrix are also, I mean, you don't have to know this fact, but for diagonal matrix also, the eigenvalues are in the diagonal. Okay, so that's why you have lambda 1 is equal to 1 and lambda 2 is equal to 1. But now comes the question: what are its? Let's go back. Eigenvectors. Can you give me one eigenvector for this? Can you give me an eigenvector for this?
One zero and 0 1.
1 0 and 0 1. Okay, so let's see 1 0. What happens? What happens? You get 1 0. And if you do 0 1, what do you get? What do you get?
One.
It's 1 1. So this is not an eigenvector. So eigenvector V1 is this 1 0. This is correct. Right? I mean, to make things clear, when you have multiplication with matrix multiplied with like something like 1 0, what is it we are trying to do is basically we pick up the first column. That's what the answer is, the first column. The column correct right now is 1 0. That's why you get 1 0. And 8 times 0 1, we are picking up the second column, and the second column is 1 1. Okay. So some tricks to see this thing. Okay. Anyway, going back. There is no other eigenvector. That's the main point for this matrix. What do I mean by no other eigenvector? No other independent eigenvector. Okay. This is the main point. And obviously there are other eigenvectors because 1 0 is there, 2 0 is also an eigenvector. But there is no independent eigenvector. And so these are called as degenerate matrices because it has less than an eigenvector, less than an independent eigenvector. Even though we have an cross matrix, we have less than an independent vectors, then it's called as a degenerate matrix. Again, I mean, I don't like this. These are again our ugly kind of matrices. Okay, so this is something probably someone asked me earlier. Right? I think someone asked me this question earlier. Can we get? Does it mean that there are independent eigenvectors? An Encryption matrix need not have an independent eigenvectors. And here is an example for that. Right. We don't like such matrices. And okay, so tomorrow we will go through some of these things. And here is an. Let me just finish it by saying the kind of matrices we are interested in, and what is special in those kinds of matrices. And I will tell this now, and I will repeat it again tomorrow so that you hear this twice. And so we will be interested in symmetric matrices. You know what are symmetric matrices?
A equal to A transpose.
Yes,
A equal to A transpose. What does it mean? If you have a matrix like this, yeah, so I'm going to write V1, V2 up to Vn here. Okay, this is my A. So A transpose is basically V1 here, V2 here. Okay. I'm saying A, these are same. So these are symmetric matrices. For example, 1, 2, 3, 2, 0, 5, 5, 1, 1. Okay, so these are symmetric matrices. As you can see, something. So these numbers are the same, and these numbers are the same, and these numbers are the same. Okay, or Aij is equal to Aji for all I and j. Okay, so these are like definitions of what is a symmetric matrix. And here's an important we call theorem for real symmetric matrix. So the crucial thing. It's a real symmetric matrix. So what in the real symmetric matrix? Real matrices, all entries are real. There is no complex number. So that is kind of matrix. I mean, for any, computer science, which problems come from natural world, the all values are going to be real. So that's the kind of natural things we work with. The real symmetric matrix, the following, these things hold. Its eigenvalues are real. Okay. You always get real eigenvalues. This confusion about this kinds of things won't happen. Okay. This such ugly matrices won't happen here. It's the main thing. So the eigenvalues are going to be real, and yeah, we're going to have an independent you're going to have an independent eigenvector. Okay, and third, most crucially, and one interesting property is that you're going to have an orthogonal eigenvector. Okay, so this is a very crucial theorem which we will see. Yeah, which will be which is an foundation for which we will see. So for real symmetric matrices, the eigenvectors are real, the eigenvectors are independent, and not just that, you're also going to have the eigenvectors to be orthogonal to each other. So you know what orthogonal? Perpendicular to each other. All the eigenvectors turn out to be perpendicular to each other. So you have n independent eigenvectors, each of them perpendicular to each other. So it's very nice property, and these properties will help you in certain ways. Okay, yeah. So we have finished our 1.5 hours. Any doubts?